In this video, I wanted to talk about buckling. So if you search for buckling in the PE handbook, there is a whole section on it, and it's kind of subdivided into two types of columns. There is intermediate length and there are long columns. And each of these is going to have its own set of equations. So for intermediate, there's more equation on this one because intermediate columns are a little bit more complicated than longer columns. On long columns, because they're so slender, there's a really clean formula called the Euler buckling equation. But for intermediate columns, you have to actually consider, it doesn't just fail by pure buckling. With intermediate columns, you have to consider yielding as well. And so there's a formula that will kind of combine yielding and buckling for intermediate columns. So first off, how do you tell if it's an intermediate or long column? Well, there's a thing called the slenderness ratio, which is the length of the column divided by the radius of gyration. The handbook just calls this R. I'm going to call it RG, just so it doesn't get confused with radius. And that radius of gyration is the square root of the area moment of inertia divided by the area. And then there's another thing called the column stress determination factor, which the handbook writes like that. And that is the square root of 2 pi squared times the elasticity divided by k squared times the yield strength. So this k squared, or this k here, is like a kind of a correction factor for the length of the column. So in the handbook, there's a table that has different, the k value depends on how the column is supported. And so in the handbook, there's a couple different, looks like there's 6 different support structures and then the k value for that. And so if your slenderness ratio is less than or equal to your stress determination factor, that means you have an intermediate column. And if it is greater, if your slenderness ratio is greater than your stress determination factor, you have a long column. To find the critical load on an intermediate column, this is the equation. So critical load equals the area, and that your area is going to be multiplied by your yield strength minus k squared over elasticity. And then we have yield strength times slenderness ratio divided by 2 pi, and that's squared. So yeah, that's how you get your critical load for an intermediate column. For a long column, it's a lot cleaner. So again, for a long column, that's if your slenderness ratio is greater than your stress determination factor. And for this, your critical load is just going to be pi squared times your elasticity times your area moment of inertia divided by k times L squared. So this k times L here is your effective length. And again, that k depends on how the column is supported. And just so we're clear, this critical load here is the load at which the column will buckle. And you can kind of see the difference here. This, in the intermediate column, you'd have to consider the yield strength, whereas if it's a long column, you don't. Okay, so I have an example problem here that should cover all that. So a solid round rod is used as a compression member in a machine frame. The rod has pinned end conditions, so this is where we're going to get our K value from, and must support a static compressive load of 24,000 pounds. The rod is made from steel with an elasticity of 29 times 10 to the 6 psi and a yield strength of 50,000 psi. The unsupported length of the rod is 10 feet. A design factor of safety against buckling of 2.5 is required. And so we're asked to determine the minimum rod diameter required based on Euler buckling. So this is telling us to assume Euler buckling. In other equations, it'll give you diameter already, and then you'll have to tell whether that's a slender column or a long column or an intermediate column. But this is kind of just giving it to us. And then B, we have to prove that Euler buckling is applicable, or I guess determine whether it's applicable. And then for C, find the actual factor of safety against yielding for the selected diameter. Okay, so for A, we know we're using Euler buckling, so we're going to use this equation, which is our critical load equals pi squared times E times I divided by K times L squared. So since we're doing a factor of safety, I'm just going to multiply that by the critical load. So we're going to increase our critical load by 2.5 times. And now we're going to solve for diameter. So to do that, I'm going to turn this I into diameter form. So it's a round rod. So our area moment of inertia is going to be pi times the radius to the fourth divided by 4. Another way to write that is pi times the diameter to the fourth over 64. Okay, so now if we rearrange this equation, we'll end up with N times our critical load times KL squared divided by pi squared times E, and this is actually going to become pi cubed, and there's going to be 64 out front. This whole thing is, we're going to take it to the 1 over 4 power, and that equals D, our diameter. So if we plug everything in, we're going to get 64 times N, which is 2.5, times our critical load, this isn't our critical load. Our critical load is the load we have applied times N. So I should clear that up in how I write that. So times 24,000 pounds. Then what is our K value? Well, if we look at this chart, we are looking for the pinned condition, and our K value is 1. It's going to be 1 times our length of 10 feet. I'm going to convert that to inches, so 120 inches squared, divided by pi cubed times 29 times 10 to the 6th pounds per inch squared. So looking at units, our pounds are going to cancel, and we're going to be left with inches to the 4th. And then when we take this root, we're going to have just inches. So this is going to give us a diameter of 2.8 inches. Okay, so for part 2, we need to determine whether Euler buckling is applicable. Another way to word that is, it's basically asking, is this a long column or a slender column? Because we assumed it was a slender column to solve this, a long column or an intermediate column. We assumed it was a long column to solve this, and now we're going to determine whether that is accurate. So from above, we can use the slenderness equation. Slenderness ratio is the length over the radius of gyration. The radius of gyration is the square root of I over A. And then our stress determination factor is the square root of 2 pi squared times elasticity divided by k squared times yield strength. So basically, we need to find whether our slenderness ratio is greater than our stress determination factor, and that's gonna, if it's greater, then yes, it's gonna be acceptable to use Euler buckling. So first, let's solve for radius and gyration. So we have pi times the diameter to the fourth. It's going to be divided by 64 times area, which is pi times r squared. My pi's are going to cancel. I guess I could have written this in radius form, and then one of my radiuses would cancel, but so 2.8 to the fourth. So this is going to come to 0.7 inches. So then our slenderness ratio is the length of the column, which was 120 inches, or 10 feet, divided by 0.7 inches. That's going to be 171.43. Okay, now for our stress determination factor. We got 2 pi squared times 29 times 10 to the 6 pounds per inch squared, divided by k squared, which is just 1 squared, times our yield strength, which was 50,000 psi. So everything's going to cancel there. And so this is going to come to, call that 107. So our slenderness ratio, or our slenderness ratio is 171.43. That is greater than our stress determination factor. So yes, Euler buckling is acceptable. If this was a no, then this question doesn't ask us to resolve it, but in the real world, you'd have to resolve it as an intermediate column. Because you'll get a different diameter, since you'll have to consider yielding instead of just buckling. So then for part C, we need to find the actual factor of safety against yielding for the selected diameter. So I'm just going to find the stress using the diameter we found earlier. So the load is 24,000 pounds. The area is pi times the radius squared. So that's 3,897.67 psi. So then our factor of safety is just going to be our yield strength over that stress we just found. So yield strength of 50,000 psi divided by 3,897.67 psi. It's going to be 12.83. So even though we have this fairly large factor of safety against yielding, because our column is so long, we're a lot more prone to buckling, and so our buckling factor of safety is only 2.5. So anytime that you are asked a question like this on the PE, it's a good idea to check. Well, first of all, make sure you're using the right equation. Make sure you know if it's an intermediate or a long column. And then it's a good idea to always check the compression yielding factor of safety. And the reason is sometimes I've seen in practice they'll have sort of a trick question where you'll just assume that all you have to consider is buckling, but it'll actually yield before it buckles. And then that's how you would solve the problem, is using either the yielding diameter or yielding factor of safety if it asks for, what's the minimum diameter required, what's the minimum factor of safety of this column, it's a good idea to just consider both buckling and yielding. But yeah, I hope this helps.